Recording.
All right. So, in this hour, I'd like to discuss the concept of the various components of a computer. And remember that computers are nothing more than complex systems, right? They have the same issues that all systems have, in that there are inputs and outputs. They do stuff inside, processing that information, and they store data, right? So you get something in, you do something to it, you get an output, and you store stuff. That's all computers do, right? Should be simple. Sadly, it's not. All right. This is the processor, right? That one has actually been disassembled a little bit. You can actually see the integrated circuit. It's about the size of my thumbnail. The reason that it's been disassembled is that they heat up a great deal. This is one of the big aspects when dealing with computers. You want a high-performance computer, you have to have very aggressive cooling. If you lift the lid on a desktop, you'll see it. It'll have a bunch of fins coming out of it. Almost like little points. That's more radiation space. If you're one of the folks who like to overclock their computers, like my son does, they actually use liquid cooling to get the temperature down so they'll operate. But this is the heart and soul of the computer. This is how it does the stuff, right? Here's main memory, right? These are cards that you put in, and you can put in as many as you want. For certain applications, more memory matters, right? For others, it doesn't. So memory can be an expensive concept. We have secondary storage. We have CD-ROMs. And I used to have a whole bunch of other things I would throw in this discussion, like tape and floppy drives and things like that. But integrated circuits are taking that over. The thumb drive is replacing everything. And they're efficient and they're cheap. And I probably lost 50 of them. The world is changing, all right? So here is a basic diagram of a computer, right? We have a bus. Now the bus is more critical than you think, all right? This is how information is transferred in the computer. And initially, the first computers I bought had an 8, the way a computer transfers information is simple. It's a switch position, either on or off, bits, 1, 0. So to transmit a single letter, you need to be able to transmit something called a byte, which is 8 bits. Well, initially computers came out, they had a single wire, and so they had to change the switch position 8 times to transfer a letter. Data transfers were very slow. The first improvement on that, as far as buses were concerned, was they went to an 8-bit bus. So now they could transfer a letter at a time. Well, if a little's good, a lot's better, right? Then they went to a 16-bit, which was 2 letters, 32-bit, and now our machines use 64 bits. So with each computer cycle, we're moving 8 letters, okay, or 8 numbers or 8 items down this bus. And everything talks to this bus. Now on this side, we have the computer side, we have the microprocessor, and microprocessors come in all different flavors and all different sizes. The faster they go, the more they cost. The greater the number of processors, the more they cost. And multiple processors mean a lot for certain applications and not so much for others. We have our main memory, right? And there's all kinds of different levels of memory. You can spend as much money on that as you want. And then there's the read-only memory. The read-only memory is something that goes into your computer when it's made, and it basically, when you turn it on, it says, hey, you're a computer. It just fires it up, gives its initial instructions, and says, go look at the hard drive. On the other side, on the output side, we've got a keyboard and a mouse, and this could include a camera, but input devices that humans control. Then we have a soft copy output, which is a monitor. Now here is a place when you're looking at computers where you can spend or make lots or save lots of money. Who wants a big monstrous monitor? Everybody's hand goes up, right? Everyone gets excited about that. Who needs a big monstrous monitor? And you start looking into it, and the people who need it is surprising. We'll talk about that later. A printer, right? How many printers do you need? Everybody wants their own. Does everybody have to have their own? No, you can centrally manage these. And you can get more powerful printers, you can get color, you can get lots of things if you centrally manage it. If you let everyone have their own printer, they've got little one-lung printers all around the campus that are a maintenance nightmare. Hard drives. You can spend as much money as you want, getting as big as you want, and now we're going to a solid state hard drive, right? Then there's all kinds of removable memory, right? I put floppy disk up there and everyone says, well, no one's used floppy disk. No, that's not true. What happens to your computer when it goes away, when you're done with it? Most of us take them to the recycler and they tear out the parts, and if they're really old, they heat them up and they take the gold and the precious metals out of them and they junk the rest. If your computer's fairly new or fairly functional, they strip it down to components and build new ones, and they sell them in the third world. So somewhere out there are pieces of a 486 that I owned that is probably in a banker's office in Indonesia or in Africa, and it's working perfectly fine. You will still see these media out there. Sadly, some people have stored important documents on floppies, put them in a safety deposit box or a vault, and left them there without the devices to look at them. So think about the storage problems that you have, and how are you storing information? If all of a sudden right now there is a cottage industry, a bunch of old retired guys who have gotten together with old Ampex tape drives and things like that, and they're converting stuff that's on tape to more modern formats because important data got stored that way, and oh, it's safe, we've got it, it's in the vault, and it's not, all right? And then there's all kinds of add-in cards you can put into a computer to make it do things. But this is how a computer is kind of architected. And if you lift the lid on them, you'll kind of see this, right? Now you start looking at the processor, right? Now, this is one core of one processor. Most modern computers have multiple cores. That means you can do many things at the same time. You can actually multitask. And the first reason people started building computers with multiple cores was so that they could play more than one note at a time with music. A goofy thing. So, central processing unit, right? This is your computer. You've got a control unit. This is your traffic cop. This moves things in and out of memory. It moves things in and out of the memory unit that's on the processing chip, your registers. This, by the way, is the fastest memory in the computer, all right? Because it doesn't have to go on the bus, right? You just go in and out. And we have an arithmetical and logical unit. This does math, only does two kind of mathematical computations. It adds and it subtracts. Everything else is just, variations on that theme. Multiplication is multiple additions. Division is multiple subtractions, and everything else you build from there. And you have the registers, the memory unit, right? Over here we have input devices, so you're controlling the processor, and frankly, the computer spends most of its time waiting for a human to touch a button. It moves very, very, very fast. All right, here's output, right? We've got these units, and we're moving information in and out of these registers constantly because this is where you're actually doing things in the computer. Registers are important. They're very fast, and because they're on the same chip as the processor, they're very expensive. All right? Now let's talk about communicating. We communicate in bits and bytes. A bit is a switch position, on and off, right? Actually, the way they do it is a positive versus a negative voltage. And a byte is 8 bits, what you need to send a letter. It uses something called ASCII code. There are 254 various letters and symbols and things like that that are in ASCII code. And there are other codes for other languages, but the bulk of the programming is done in some form of English. And so you count like this, 0 and 1 are the same, but what's 2 is 10. What's 3 is 11, and it's all ones and zeros. Now, it's not rocket science why humans count in base 10. We count in base 10 because we have 10 fingers. And humankind started doing math this way. And certain times I still do it that way. But 10's a bad thing for a computer. It's very hard to set the gradations so that you can determine whether it's a 3 or a 4, right? You try to set voltages, so that doesn't work. Analog computers struggle with that all the time. So positive voltage versus negative voltage, easy to detect, ones and zeros. That's why it goes that way. Then we talk about how much information you're storing, right? Now, a kilobyte, right, is 2 to the 10th power, and it's 1,024 bytes, all right? A megabyte, now we're starting to talk about numbers that people talk about, is 2 to the 20th, and that's 1,048,000 and change bytes. A gigabyte's 2 to the 30th, a terabyte's 2 to the 40th, and a petabyte is 2 to the 50th, all right? You know, and you trot these numbers out and people go, well, gosh, people don't have that much storage. I had the good fortune to go visit the folks at Micron here just a couple of weeks ago, and they're moving petabytes of data on a regular basis. They're storing all kinds of integrated circuit designs. They're huge. And they talk about managing data centers with 20 or 30 petabytes of data. They figure Micron manages 100 petabytes of data. It's truly outrageous. Then there's speed, right? We all talk about how fast your computer goes. Everybody wants something that goes faster, but we don't know what we're going faster to do, right? I mean, in a car, we got to figure it out that, you know, you can get places faster. It happens the same way in a car or in a computer, right? If you go faster, you can do more. Now, we measure something called the machine cycle. It's the time it takes the computer to do one thing, like fetch information, decode information, execute a command, or store something, right? And computer time. Computer time is in fractions of a second. Computers move very, very fast. A millisecond is 1,000th of a second. A microsecond is 1,000,000th of a second. A nanosecond is 1,000,000th, and so on, right? You get smaller and smaller and smaller, time gradations. Why does this matter? Well, modern computers are running up against a problem that we never thought would happen. Okay. It's the speed of light. In a vacuum, light goes at about 300,000 kilometers per second. In a wire, it goes about 200,000 kilometers per second. So in a nanosecond, 1,000,000th of a second, light goes 6 feet. Okay, that's enormously small when you think about it, because we have computers that have a 3 gigahertz clock. So in the time that computer does one thing, light can travel 2 feet. That means everything in that computer has to be less than 2 feet away. And it's actually worse than that, because you have to have about half the time to sense the change. So in a 3 gigahertz computer, everything has to be within a foot. So computers have to be smaller to go faster. To go smaller costs money, all right? They're harder to work on and a whole bunch of things. So the speed of light is controlling the speed of computers. Now, that's about to change. You know, we talk about the way things are changing. The new thing on the horizon is called a quantum computer. We are looking at the interactions of molecules over very small spaces in multiple different dimensions. And I'm rapidly getting to the area where I don't understand it at all, but performance will take, you know, several orders of magnitude increase when those become commonplace. IBM has one. I believe the NSA has one. Google has one. And they work. They're functional. All right. So we measure hertz, or this clock rate, you know, using megahertz, gigahertz, right? Megahertz is a million, and gigahertz is a billion. And we slice up seconds, right? Again, a nanosecond, a billionth of a second, like 3 machine cycles for most computers. Light travels 6 feet. In a standard computer, it's going that far. And look at your computers where the processor is, right? Everything's within that radius. There is some discussion as to whether or not future computers are going to be spheres, just to handle the speed of light. All right. Now, storage. Okay, here's another area where we can spend all the money we have. Storage, right? And we can do it internal, we can do it external. Memory chips are expensive. There are many, many different kinds of chips, right? Here's a Micron DDR SDRAM. There are a whole bunch of different kinds of memory. They showed us some prototypes of high-speed NAND RAM when I was at Microsoft that operate very fast and are very small, and they're not volatile. That means when the power goes off, they still remember stuff.